right, everyone, I've been instructed to kill time. Also, we have a distinguished external guest today, and whenever there's a distinguished external guest, it's customary for someone you already know to come up and tell you their opinion of the distinguished external guest. So I'm going to tell you my opinion of Brian. How much time do we have? Brian's prominence and importance to the Java community goes back decades. One of the ways that you are probably familiar with Brian is he is the lead author of Java Concurrency in Practice, which is truly one of the essential reading books for Java programming. We think about 8 years ago, he came into the role of lead Java language architect at Oracle. And starting a few years after that, I've had many chances to work with Brian in several of the expert groups deciding the final form of language features for Java. And the thing that I've learned through this process is that making language design decisions for a language with as many existing users as Java already has and as much existing background is essentially an impossible task. It basically, to make a decision that you know is the right one, first of all, explodes into incredible complexity, many nuances, and is essentially impossible to make those decisions. I really cannot imagine anyone more equipped to lead this effort than Brian, and I've been repeatedly very impressed with his stewardship. Maybe that was more flattering than it's supposed to be. Maybe it was supposed to be more neutral. Big fan of Brian. With that said, Brian Goetz.
Just get this mic'd up here.
All right, thank you, Kevin. So someone's going to try to figure out why the AV only has half a brain and is only projecting on one of the monitors. So what I want to talk about today is sort of where is the Java language going, and some of the decision factors behind the decisions that we've made about what features to do. Because as you can imagine, the list of possible features we could add to Java is infinite. And we can probably do realistically like 6 of them in the next 10 years. So winnowing an infinite list down to something that small is a difficult task. This is how you know I work for Oracle. Safe harbor slide. I'm not an imposter, I promise. So you know, as Kevin said, Java is in an interesting position because it has been around for a very long time. Java's been around almost 25 years. I've been programming with Java almost 25 years, which is terrifying. And you know, one of the things that I've noticed over those years is people just love to say, "Oh, Java is done for. It's dead. It's an old man's language. It's the new COBOL." And it somehow has managed to hold on to its popularity. Java is still, by some measures, the world's most popular programming platform. And we would like that to be true for the next 25 years as well, if we can do anything about it. And our super secret plan for how are we going to do that is stay relevant. Stay relevant to the problems people want to solve. Stay relevant to the hardware people want to run their programs on. Thank you, JC. Yeah. Exactly. And keep the promises we made to our users. I mean, code that you wrote and compiled in Java 20 years ago still runs for the most part on modern JVMs. And that's why people continue to program in Java, because we don't undermine the investment that you've made in your code. And one of the things that we have done to accelerate this process in the last few years is to co-evolve the language and the JVM together. This was something that wasn't really practical 10 or 15 years ago when we did, say, generics. That's become more practical, and it's something we're getting better at. So, you know, I talked about keeping our promises, and the prime directive from our perspective is compatibility. Code that you wrote 20 years ago should just work today. It should run faster, but it should just work. And you only get one chance to break trust with your users. If we break your code, that's when people start thinking, well, maybe I should rewrite this in another language. And there was a question earlier about why does X take so long in Java, where X could be almost anything. And one of the reasons for that is that evolving the platform in a way that keeps the promises that we've made over the last 25 years, of which we've made quite a few, takes longer, costs more, constrains the options. Sometimes we pick something that Sometimes we pick something that wouldn't be our first choice if we were designing from a clean sheet of paper, but is the sensible thing to do in the context of there's already, hundreds of billions of lines of Java code out there, and we don't want to break any of that. And, sort of a good example of the complexity of, hey, it's working. Excellent. Thank you. A good example of, sort of the complexity of this and why some of these things take so long is if you think back to 2004 when we added generics to the Java platform, we didn't want to have a flag day where everybody in the world had to recompile all their Java code. So we had to do it in a way that, that you could migrate gradually. We had to do it in a way that a given class could be generified now, later, or never, that clients didn't have to generify at the same time as a class. And that basically made the problem about 10 times harder. And so it took quite a bit longer to do, but the result was you got graceful degradation of the boundaries. We had no flag days, and you didn't have to set your engineering calendar based on what Sun's priorities were at the time, right? It would have been terrible if the whole community had to drop what they were doing and do a bunch of, make a bunch of changes to their code just because the language had changed. We want you to do that on your schedule when it benefits you, when you feel it delivers value to your code base. And if the answer to that is never, that's fine. Keep doing it the old way. Lambdas were sort of a similar example where we did something that might have been suboptimal from a clean paper perspective, but that made tremendous sense in the context of how people program in Java. And that was instead of adding function types to the language, we, Lambdas are typed using single method interfaces. And that's a little bit weird, but one of the things that did was it allowed 20-year-old libraries that had never heard of Lambdas to be used with Lambdas on day one without being recompiled. And that's a big deal. That would not be a big deal if we were starting with a new language, but because we're starting with an ecosystem of library and user code out there that's enormous, this was a very big deal indeed, and it was worth distorting the design a little bit to get that benefit. The other big principle that we sort of apply when we're thinking about language evolution choices is language features are forever. We don't get to say, oops, my bad, we're taking this language feature away. We sometimes get to deprecate library methods or library classes after a very, very long time. Language features, it's not practical to deprecate them. And so you have to get it right the first time. And not only do you have to get it right, but you have to not foreclose on other valuable options. Every language feature interacts with every other language feature, including the features you haven't done yet. So, and each language feature adds weight and complexity to the language that constrains what we can do next. And so if you don't know what the right thing to do is, the right thing is to do nothing. And in the last talk, a gentleman sitting over here was asking, how come it's taken so long for Java to catch up with coroutines and such? I'm paraphrasing the question. Part of the answer is, I am so glad that we didn't jump on the async await bandwagon when that was the hot thing. What a mistake that would have been. So the first mover advantage is often not an advantage. We had, we didn't know what the right thing to do was. The popular thing would have absolutely been the wrong thing to do. So I'm really glad we didn't do that. And we had the luxury of being able to think about it and say, well, what really would be the right thing, not just for the problems of this year, but the problems of 10 years from now, 20 years from now. And I think we are working on the right thing now. So yes, other languages are going to go out and experiment and do some wild and crazy things, and some of them will be brilliant and some of them will be mistakes, and we get to learn from all that, and that's awesome. So, we have to be a little conservative, and that's, frustrating to some people because we're playing a long game, but it's important to remember that language features, as much fun as they are not ends unto themselves. They're a means to an end. And that end is not about language features. It's about programs. It's about making it easier to build and maintain reliable programs. That's what we view our job as. And we want to give people tools to make it easier for them to do that, so that the investment that you make in your programs is something that you'll be able to reap over a much longer period of time. And, I keep using the word evolution, and I really think that's what's going on. Languages have to evolve or they die because, languages grew up in response to their environments. What kind of problems are they trying to solve? What kind of hardware are we running on? And when those things change, the sort of optimal place to be is going to shift as well. And if you don't evolve, out of the niche that made sense 20 years ago but doesn't make sense now, you're going to be left, left to history. And so, I sort of think about it as, there's an ecosystem where, programming languages are the predators and programming problems are the food supply. And, hardware and software development practices are sort of our environment. And these things are all changing over time. And, we can try to do something that's optimal for today, but we know that these are moving targets and we're going to have to evolve. And on the other hand, if we move too quick, we may do the wrong thing and we end up tying a weight around our neck that we have to carry around for a long time. So it's a tricky balance to maintain. One of the things that we've done recently is we've changed the cadence at which we deliver Java. It used to be we had these big, massive releases every 2 to 4 years. We pretended it was going to be 2, and then it turned out to be 3 or 4 because life happens. And that was difficult for users and it was difficult for us. And about 2 years ago, we moved to a 6-month time-driven release cycle where we ship every 6 months like clockwork, and late bind features, when they're ready to board the train. And this has been a huge success from my perspective. Not only are we able to deliver innovation, more rapidly, which is great. It also means that all of the release management overhead that you used to have to do when the train was only leaving every 4 years, we don't waste any time on that anymore. We spend basically all our energy now doing engineering work, and when a feature's ready, it boards the train. And it's been incredibly smooth. And it's also kind of taught us a little bit how to take big features and break them up into smaller features, which has also been a big help. So this has been, a big improvement in how we deliver, but it also is a change for how Java developers have to think about adopting new versions of Java. It used to be, you basically got this engraved invitation because there was some big feature like lambdas or generics that was so attractive that there was no choice but to upgrade. Now, there's still the same amount of innovation going on, but it's being sliced up in smaller increments and delivered more uniformly in time. And as a result, there aren't any single huge things that are coming along that are going to force you to upgrade, but there's a lot of little things, that are going to improve your life. And so we kind of have to change our way of thinking about adopting new versions. And because we're releasing more frequently, features go through a round of what we call preview before they are made permanent parts of the platform. And this is a kind of an experiment where we're not quite sure that we've exactly figured this out right, but it gives us an opportunity to put features in the JDK behind a flag. You have to say -enable preview to turn it on, but there is a full specification, implementation, test kit, IDE support for them. They're real features, and you can try them out and provide feedback before the concrete gets poured. And we think it's been pretty successful. It's already saved us from making at least one big mistake, so I count that as a success. And this is, so what you'll see is as language features roll out, they will go through 1 to 2 rounds of preview before becoming permanent. And it's also a signal for what's coming down the road. If something is preview now, that means we've really done like 99% of the work. This is not an experimental, hey, let's try this and see what happens. Okay, so let me talk about some of the initiatives that are going on in the pipeline. The pipeline for features. For future features is probably better now than it's ever been before, and it can be actually a little bit overwhelming to keep track of everything that's going on. We organize into projects. Each project has a theme. So Project Amber, you can think of this as productivity-oriented language features or right-sizing language ceremony, we like to say. And most of the smaller but fun features that you've seen are coming out of Amber. Project Valhalla is a much bigger thing. It's a much longer term thing. It has to do with rebooting the way that the JVM lays out data in memory in a way that will be friendlier to modern hardware, because hardware has changed dramatically over the last 30 years. And the primary way we're going to accomplish that is through value types and through specialized generics. And this is a long-term game. We've made a lot of progress on it. We're not there yet, but it's coming along pretty nicely. Loom, you just heard about in the last talk, so I won't talk about that too much. And then the other one that's interesting, if you're doing any native interop, either data in the native heap or calling C code, is Project Panama. And that's also made huge progress in the last year. So there's a lot going on, and it's likely that each of these features will be generating, each of these projects will be generating features over the next year that you'll be hearing about. So I'm going to talk mostly about Amber today because programmers love hearing about programming language features, and I like talking about programming language features, so works out. Some of these features have already shipped. Amber delivered local variable type inference in 10, switch expressions in 12, text blocks in 13. 13 is going GA, I think, this next week sometime. I don't even know when because it doesn't matter. It's just, the train is rolling. And I'll talk about some other features that are coming up in the next probably year coming up out of Amber as well. So from my perspective, this one is old news, but I'm going to talk about it because it's not old news for you because you guys are still working on Java 8, which you should probably do something about that. It's actually funny, I spent several years of my life stewarding Java 8, and part of what I had to contend with during that time was convincing the world that Java developers were actually up to the task of dealing with lambdas, and that this wasn't some crazy alpha geek who's grabbed the steering wheel and driven the car off the road, which, believe it or not, people really thought, and we had to do a lot of work to convince the world that that lambdas and streams were a sensible thing to do in Java. And it's kind of funny that only like 6 years later, 8 is the new legacy that everyone is stuck on and thinks they'll deploy on forever. Time moves fast. But since then, we've been working, we've been doing stuff. So one of the things we did in Java 10 was type inference for local variables. So Java's had type inference for years. Since Java 5, we had type inference for generic type variables. In Java 7, we added it for constructor parameters. In 8, we added it for lambda parameters, lambda formals. And in 10, we added it for local variables. And you're all familiar with this from other languages. You've seen this in Scala or Kotlin, where if the compiler can figure out the type of a local variable from the type of its initializer, you can lead the manifest type and just say var variable equal initializer. This isn't whole program Hindley-Milner type inference. This is local. It's not even type inference. It's type synthesis, where you look at the thing on the right side, you compute a bottom-up type for that, and you say that's the type of the local variable. And this is kind of a funny feature in the sense that it was the most commonly requested feature we got from people saying, well, why don't you add this to Java? And yet when we finally said, like 10 years too late from some people's perspective, when we finally said, okay, we're going to add this to Java, immediately the haters come out from the woodwork saying, oh, you can't do that. That would be terrible. Oh, you're just encouraging bad programmers to write bad code. Like they need encouragement, right? And there was this doomsday scenario of unreadable Java code, that was professed, and in reality, we've been shipping this for a year and a half, and the world hasn't ended, and people are starting to develop an intuition of when this makes your program more readable and when it doesn't, and use it when it does, and don't use it when it doesn't. It's kind of like the judgment thing. Some developers don't know about that, but it's like I said, it's not an earth-shaking feature, but it allows you to eliminate some potential noise from your program. And if you look at what's going on in these simple lines of code, there's three things. There's a type, there's a name, and there's an initializer expression. The most important thing is the name, right? Because that's where the programmer actually used creativity to say what's going on in this program. And so if you've chosen good names, which we all do all the time, right? Good. Why not bring that sort of front and center into the user's line of vision? So sometimes the type information is really important. We're not saying you can't put it in there explicitly, but if it's not adding value to your code, you don't have to use it. So, all right, what are the rules? This works for local variables. It doesn't work for method return types or field types for obvious reasons. People love to say, oh, this is syntactic sugar. It's not actually syntactic sugar. There's some complexity going on here because the Java type system isn't trivial. There are some weird types like intersection types and capture types and anonymous class types that get special treatment. So, for example, you would think that the type of this.get class is just class of question, but it's actually actually a much more complicated type that comes out. It's a class of some capture of question at a particular point in the program that you actually can't see in the source code, because it's similarly, if you said, give me a list of 1, 2, and the string 3, you might think that would be a list of object, but it's actually a tighter type, a list of question extends serializable and comparable. And so, the benefit of this feature eliminates some noise from our code. One of the disadvantages is it exposes people to the type system that's been there all the time that they just didn't know about and might have to actually deal with. But like I said, there was a lot of debate over this, a lot of noise over this, and then once the noise died down, people seemed to be figuring out how to use it. We did write a nice style guide for when to use this and what to use it for and when not to. That we think is a sort of successful way to evangelize new language features. We'll continue to do that for other features. All right, let me talk about another small feature. And this one's an interesting one because it evolved out of a bigger feature, and that is switch expressions. So most of the switch statements that you encounter in real code bases kind of wish they were expressions, but they can't be because switch is a statement. And so they sort of simulate an expression using a statement, which is indirect and verbose and error prone. And people love to hate on the need to break out of each arm of a case. But not only is that annoying, it's a place for bugs to hide. It's easy to forget, and now you've got a subtle bug that your test might not catch. And we had been exploring enhancements to switch through the context of a bigger feature that I'll talk about in a few minutes, which is pattern matching. But we realized that even though we weren't done with pattern matching, we kind of were done with the switch stuff, and it was useful for people to use as is, so we moved it forward in time and previewed it in 12. And as an example, here's a typical kind of switch statement that that approximates an expression where you have to assign to a common target in each arm, and woe be unto you if you forget to do that in one of the arms. And then annoyingly, you have to say break in each arm, and that's annoying. And then the final insult added to injury here is you're switching over an enum. You've covered all the enums. The compiler knows you've covered all the enum constants, and it still makes you write a default clause that what's it going to do? Of course, it's going to throw some exception. And so this is a simple thing that the language kind of makes you do in a very roundabout and complicated and potentially error-prone way. And if we replace that with a switch expression, we're able to write that a lot more concisely and in a much less error-prone way, where we can have multiple case labels, and there's the thing on the right side of the arrow is a single expression or a block. You don't need to break at that point. And if the compiler can prove that the expression is total without having a default clause, then it says great. And it will it'll insert into the bytecode a default clause just in case someone adds a new date of the week after you've compiled your program. It's basically the same exception that you would have written by hand, but the compiler does it for you, which is better. And it also provides a tripwire that if through separate compilation, this enum evolves, you actually get notified the next time you try to compile. So this is kind of the code you had in mind when you started to write the horrible code in the previous slide, but you had to write it the horrible way before. This is actually two separate enhancements to switch, which are kind of orthogonal but work together. One is use it as an expression or as a statement. The other is the newer kind of case labels where you can use the arrow form instead of the colon form after the case, and then it knows there should be exactly one thing on the right-hand side of that. And therefore doesn't require you to break. And you can use those streamlined case labels with switch statements as well. It's they work nicest together when you use both of them, but it's basically two orthogonal features that work well together. And like I said, this sort of started out when we were working on pattern matching. And so when we get to pattern matching, it'll all work nicely together, but it's something that we were able to release earlier because we had more opportunities to release. A feature that we added in JDK 13, which, like I said, is shipping this week or next or something like that, is what we call text blocks, or what most people call multi-line strings. And this is again one of those persistent irritants that people complain about all the time, and it's not a deep feature, but it's again, we focus on these things not because we care so much about reducing boilerplate. I mean, I know programmers care a lot about boilerplate, and code should be easy to write, but it's much, much more important that code be easier to read. Because code that's hard to read is code that has bugs that you haven't found yet. And so, one of the things that you have to do with existing string literals, as you all know, is if you want to have a multi-line string in Java code, you have to mangle it up into multiple strings with explicit new line escapes. And that mangling, if you're lucky, the IDE does it for you. If you're not lucky, you have to do it manually. And when you do things manually, you occasionally make mistakes, and which you discover at runtime. And similarly, these mangled strings are harder to read. It's harder to tell exactly what's going on because there's all this extraneous noise in it. So ideally, it would be nice if I could just cut and paste a snippet of JSON or SQL or HTML or whatever into my Java code and say, I want that to be a string. This was actually a feature where we designed it, and it was we almost said, let's preview it. And then at the last minute, we said, no, we don't like it. We're pulling it back. And we spent another 6 months improving it. And the improved design is much, much better. And so this is sort of another hidden benefit of the more rapid cadence, is that the cost of saying, no, this feature isn't ready, is a lot lower, and it gives you an opportunity to avert a mistake. So it's pretty straightforward. This is what we have to write today. So the code and the stuff in red is extraneous garbage that we'd like to not have to look at. A text block, big surprise, uses a different delimiter and uses actually the same escape set inside. So you can still use \n and \r inside the body if you want. The delimiter is in this case 3 quotes instead of 1 quote. This is actually kind of an interesting feature design because we did a survey of what other languages do for raw strings and multi-line strings. And when we do this, and we do this a lot, we look at how do these 15 languages solve this problem? You very often see big clusters of 8 of them do it this way, 6 of them do it that way, and then you've got this one weirdo doing it some other way. With this feature, we looked at like 15 languages and we found 15 different ways to do it. And you can be sure that each of those 15 languages had strong proponents by why this was the one true way. And in reality, each of these different designs are a statement of what's important in that community. Right, and a lot of them are trade-offs of how simple do you make the easy case versus how possible do you make the the corner cases. And so very often, like I said, you'll see big clusters and you'll say, well, it seems like the world has converged on this. VAR is an example of that. Everybody picked the VAR token. We could have picked something else, but why why pick a fight with people's intuition? But this was something where literally there were 15 different ways to do it in 15 languages. And so, of course, we did it differently. But we did draw inspiration from a number of them. Now, one of the things that happens, when you convert the previous code to this is, what about all that white space like underneath where it says string HTML? It's nice that I was able to indent the snippet of text with my program, but now I have a bunch of extra white space in between, in the middle of my string, and we probably don't want that. And we certainly don't want that to change every time I re-indent my program. And so the most interesting design discussion about this feature was, by what algorithm should we decide that certain white space is incidental versus certain white space is essential? This was Kevin talked about how we collaborate on language design, and one of the super useful things that's come out of this collaboration is you guys have this huge repository of Java code over which you can run static analysis and say, what do people actually do? And the data that we got out of this process was really useful in pushing us towards, all right, now we see what the common cases are and what the corner cases are, and we picked something that that tried to balance those things. And I think it's pretty good, but it might not be perfect, and it's a preview feature. So if you go out and try it, and you find a case where it does the wrong thing, we have a chance to fix it before it goes public. So that's one of the points of preview features, is so that people have a chance to try these things out before it's too late to make any changes. All right. So let me talk about what's coming soon, and by soon I mean in the next year soon. not in Java 13 because that's about to ship, but like maybe Java 14, maybe Java 15, which is, a year away. So a lot of classes that we write are just dumb wrappers for data. And we all understand, the rigmarole you have to go through to write a well-behaved, domain class. There's instructions in effective Java. You write, private fields in a constructor and accessors and equals and hash code and toString. And if you're lucky, you have a code generator that hides that all from you, so you don't have to do that. But it makes sense to try to hide that, but it makes more sense to try to get rid of it. And what's going on here is I think we're coding at the wrong level of abstraction. We're modeling data with classes rather than having a language have a notion of data. And then you don't have to model, you don't have to go through all this modeling overhead of mediating access between the API and the data, because the language knows that this is a class that is just a container for the data. And it's able, to derive from that, some sensible API idioms, so that you don't have to do everything by hand. And this is something that we've done before in Java. If you remember when enums were added in Java 5, it was possible to get the benefit of enums, before Java 5 by writing in a particular coding pattern. And it was verbose, but it was doable. And enums eliminated all the clutter of that by allowing the programmer to make a semantic statement. The semantic statement is, I know where all the instances of this class are. And that was the programmer giving up some control. The programmer saying, I cede control over instance instantiation to the runtime. And by giving up that control, the runtime is able to say, okay, well, if you're going to let me be responsible for this, in return, I can generate the constants for you. I can generate equals and hash code for you. I can generate serialization code for you, all of that, because I know more about your program than if it was just a bunch of static final fields. The same thing is going on here. If we're able to say this class is just a container for its data, then the compiler can reason about it. And the thing we've given up is the flexibility to decouple the representation from the API, which sometimes we don't want to do, but sometimes is a perfectly reasonable thing to do, and it makes our program simpler. Okay, so we'd like to write classes like this, but you can't actually do that. You have to do this. And remember what I was saying about, I don't care how hard it is to write code, right? This is like code that your code generator or your IDE can generate for you. But I care a lot about how hard it is to read this class. Because to read this class, you look at it and say, okay, yeah, that's doing nothing, that's doing nothing, that's doing the obvious thing. And you spend all this time to discover that you didn't have to read it, which is kind of a waste of time, right? And you've seen, again, similar mechanisms in other languages. Again, this was one where we looked at what does Scala do, what does C# do, what does Kotlin do, and they all did different things. And the different things that they did reflected different priorities about the importance of mutability, for example. The corresponding feature in these other languages differ subtly. And what Java does here differs subtly as well, because we came at it with different priorities as well. So you declare a record like this, you can think of it as a nominal tuple, and the compiler infers an API for you. Constructor, final fields, accessors, equals hash code toString. If it's serializable, safe serialization code that round trips back through the constructor, so that if someone forges a broken instance, it will get caught in the argument checks, validity checks in the constructor, etc. But it's a class, and you can put stuff between those braces. And if you don't like the implementation of the constructor the compiler gives you, you write your own. And if you want to write other methods, you want to have type variables, you want to implement interfaces, knock yourself out. It's a class, but you've given something up. You've given up the ability to decouple your data representation from your API. And in return, you get all these goodies. So like I said, this is a feature that we're pretty much done on the design process with. So it's in the sort of, preparing your order for shipment phase of the program. And we are hoping very much that this will make 14, although it's possible it won't, but we are certainly hopeful. So like I said, it's very pleasant to get rid of that boilerplate, and I certainly don't miss it, but it's not a feature about boilerplate. It's about about program semantics. You're saying, I am a carrier for my data, and the language and frameworks are able to rely on that to to reason about these things. And like I said, it's a trade we've made before. I think enums were a pretty good feature. I think the benefit of records is similar. We'll probably see more records than we saw enums, but it's basically the same game being played over again. And a feature that goes very nicely with records is sealed types. So those of you who have programmed in functional languages hear records and sealed types, and really you're thinking product types and sum types. So records give us one half of what are called algebraic data types. They're products, Cartesian products. And the other half, which is sum types or discriminated unions, is also useful. So a discriminated union is simply saying a shape is either a circle or a rectangle and nothing else. And by saying and nothing else, you get some benefits, just like in the switch statement we had earlier, where the compiler was able to say, you covered all the days, I'm not going to make you provide a default clause. Compiler can do similar kind of reasoning when it knows about, well, you had a shape, you covered the circle case, you covered the rectangle case, that means you've covered the whole story. And it's also really useful for platform APIs, being able to say, here's a class that has multiple implementations, but I know where they all are, and therefore I can guarantee that they maintain certain invariants. That's something that's more important to us, and probably important to customers like Google who build their own internal libraries, less important to application developers, but it is important as well. So you can declare a type as sealed by saying sealed. You can provide an explicit list of the subtypes that are permitted. The compiler will infer those if it can. So if they're all being co-declared in one compilation unit, the compiler will figure out what the subtypes are. If you want to be explicit, you can be explicit. And so the shape hierarchy that I talked about a few minutes ago is, it can be declared this way, where you say, okay, well, I have an XY point, I'm going to declare that as a record. And then I say there's a thing called shape, which a shape can be either a circle or a rectangle. And a circle has a center, which is a point, and a radius. And a rectangle has 2 points that are coordinates. And that's it. That's the whole shape hierarchy. So records have a lot of use cases, for cleaning up the code that we write every day. So for example, it comes up fairly commonly that you'd like to return more than one thing, but you don't want to declare a whole new class just to carry the data from a method to to its caller. But by reducing the overhead of declaring an aggregate, it makes people more willing to actually declare aggregates, right? So if you had an API where, say, you were picking the minimal element out of a list, you might, in the old days, you might be inclined to write two methods, a min method and a max method, and they each return int. And that's easy to write, except that if you want the minimum and maximum, it's a lot easier to gather them together with a single pass over the data than make one pass over the data for the min and another pass over data for the max. One of the reasons people didn't write the more sensible API is it was too much work. By reducing the overhead of declaring aggregates, people are more likely to write the correct API. And this is something that we saw, for example, like earlier I alluded to the debate over whether being able to say var makes your programs better or worse. One of the hidden ways it makes your programs better is that by reducing the overhead of declaring a local variable in the middle of a computation for some intermediate result, it means you're more likely to do that. And that makes your code more readable because you've named the intermediate result. Whereas if you had to write this big hairy type in front of it, you would just inline it all together and you'd have this big 19-level nested deep chained expression because that was the easy way to write it. It isn't necessarily the easy way to read it. So by lowering the overhead of writing it the right way, people are more likely to write the right code. Similarly, one of the most common questions about streams that you see on Stack Overflow is, I want to do something like, sort something by some derived key, but I don't want to derive the key every time I compare it because that's inefficient. And again, they're looking for a way to do that without, without defining a whole separate abstraction. Well, records can be local to a method. just like classes can be local to a method. So, here's an example of, I have some list that I want to take, the top end by some derived quantity. So I declare a little record to hold basically the tuple of the person and their score. And then I can use that in this stream expression where I say, well, the first thing I do is compute the tuple for every one of them. And then I have, I make a comparator to, compare by the, the hash value or the score value or whatever. That should be person X : score, typo. And then the last thing I do after I pick the ones out I want is I project away the extra garbage information that the user didn't want. And again, by reducing the overhead of sort of doing it in the right way, people are more likely to do it the right way. And lots and lots more use cases for records and sealed types. Any kind of tree node, anything you would have to describe a data structure layout, anything for passing data between one layer and another, compound map keys, messages and actor systems. It's one of those things that once you have it, you wonder how you lived without it. Which sort of brings me to the sort of bigger feature that where a lot of this came from, which is pattern matching. Now, if any of you have programmed in functional languages, you're used to pattern matching, and you might be forgiven for thinking that pattern matching is actually a functional feature, just because you only see it in functional languages for the most part, but it actually fits very nicely into object-oriented languages as well. So what pattern matching does is it takes three things that we do all the time together and combines it into a single primitive, which is I'm doing some kind of test. If the test succeeds, I'm going to extract something from it, and I'm going to bind that to a fresh local so I can use it. So we write code like this all the time. If something's an instant of integer, then cast it to integer, and then bind it to a local and use it. And there are some irritating things about this, right? I have to repeat the type, which is repetition is an opportunity for bugs to hide, right? And I'm also, you could argue that the whole cast is, why do you have to do it? What else would you possibly do after test if something's an integer? The only other thing you could do is cast it to something else because you cut and pasted the code from somewhere else. So this is not the language helping you. This is the language daring you to make a dumb mistake. And so that's not good. So it's irritating and it's error prone, right? Trifecta. And there's a million suggestions of how to make this better, right? Oh, just do flow typing. But we think pattern matching is a richer and deeper answer to that. So a pattern, there are many kinds of patterns. The simplest kind of pattern is a type pattern. Type pattern looks like a variable declaration. Integer, int value, a type and a name. And it's not by accident that it looks like a variable declaration. And then you can put one of those things on the right side of an instance of, where you say, if object instance of integer, int value, and it's going to fuse those three operations together. Are you an integer? If so, cast to an integer and bind the result to int value. So not only does it make the boilerplate of the cast go away, but it brings the business logic sort of to where you can actually see it. Now, there are other kinds of patterns. I'll get to some of those in a minute. It's a much deeper feature than just this, but this is sort of the entry level pattern matching. And here's an example of where you would use it. If you look at the code that your ID generates for it equals, the control flow is awful. It's if this, return false. Otherwise, if that, return true. Otherwise, return this other thing. And you don't want to read that code. No one wants to read that code. You'd like to be able to write it as a single expression where you say, is the other thing the right type? If so, bind this new variable to that type, and then compare all the fields. And that's just a single Boolean expression that's much easier to read and much harder to mess up. So we've been coding around the absence of this for a very long time. And so we will probably do this in phases. We will probably do type patterns and instance of first, and then switch a little bit later, just because switch has all these weirdnesses associated with it that we have to deal with. But there's a lot of code that would like to be a switch, but can't. right? So we write these chains of instance of, and it's unpleasant in like every possible way, right? There's the repetition of the instance of in the cast. There's the repetition of asking the same question in a slightly different way 17 times. There's the repetition of assigning to a common variable and hoping you got it right each time. So, we write this code because we have to, not because we want to. So if we turn our case labels into patterns, we can get rid of a lot of that noise. And this is, that's a good start. So instead of saying if x instance of integer, I say, switch on x and say case integer I. And if it selects this case, then I will be bound and definitely assigned in the statements that follow. But we can do better. And we saw earlier with switch expressions that switch statements like this would like to be expressions. And in fact, we can easily use these two features together with pattern case labels and switch expression. And then you arrive kind of at the code you had in mind before you started writing that horrible chain of if then else, right? So, one of the reasons why we picked these features is they work together. And they work together in some surprisingly deep ways. So let's talk about how records and pattern matching work together. One of the things we said about records is they are transparent carriers for their data. That means the language should know how to scoop the data out and use it. And so we can have, just like we had type patterns, are you an integer? We can have deconstruction patterns for records, are you a point? And if the, and the test is instance of point, that's the same thing, but the conditional extraction after the test succeeds is not just cast it to a point, but scoop out the components of the point and bind them to variables. And so, for example, in our shape hierarchy, I can say if shape instance of circle, and then I have some things that look like variable declarations. They're not quite variable declarations. Inside the parentheses, var center, var radius, where it says, are you a circle? If so, cast a circle, get the center and radius out because they're records, and I know how to do that. And there'll be a way to do that for things that aren't records, but we'll get there. And bind them to these local variables, and by the way, infer their type from the class declaration. And there's no magic here. These deconstruction patterns are just class members like constructors. They're in fact basically the opposite of constructor. Constructor takes some data and gives you an object. Deconstructor takes an object and disassembles it into the what did you present to the constructor when you made the thing. And so we're not doing any kind of magic like guessing based on field names or anything awful like that. And records would get these for free. And if you want to declare these for ordinary classes, you could. So here's putting all these features together. It's kind of nice. Let's say I have a shape and I want to compute the area of the shape. So I have to switch over the different kinds of shape. And I know that the only two kinds in this hierarchy are circle and rectangle. So I switch over my shape, case circle, declare placeholders for my center and radius, and compute pi r squared. And if it's a rectangle, declare placeholders for my bounding points and compute delta y times delta x. And it can't be anything else, so I don't have to say anything else. That's a lot nicer than what you would have had to do by hand with instance of and cast and or visitor pattern. These features work pretty nicely, and pattern matching is actually a pretty deep rabbit hole. And to kind of illustrate how deep a rabbit hole is and how this really is something that we've been missing for a long time and just didn't know it. We've been working around the absence of this in OO APIs for a long, long time. If you look at the Java Lang class, it has two methods. Well, it has a lot of methods, but it has two methods that work together. Does this class represent an array, and get me the component type of that array? And there's a precondition that says, don't call that other one unless this one returns true. Well, that's an API design pattern that is a mistake waiting to happen. It's more work to define a defensive API like that, and it's easy to misuse. Whereas if these two API points were one pattern, you couldn't misuse them. You'd say, if the class is an instance of array class, var component type, then you would never have the opportunity to ask for the component type if you weren't already an array class. And so this is an API design idiom that we've just been missing for 25 years and didn't notice. And once you notice it, you see it all over the place. It's a cool feature, but it goes a lot deeper than you might think. So, all right, I'm going to switch gears here in the last few minutes and talk about Project Valhalla. Project Valhalla is more about performance than about programmer productivity, but performance is important too. Over these last 25 to 30 years, the hardware we run on has changed a lot. The relative cost of a memory fetch and an arithmetic op has expanded by a factor of almost 1,000. 30 years ago, memory fetch and an addition or multiplication they're both on the order of a few cycles. Now, a cache miss out to main memory is like 300 cycles, and a cheap laptop processor can issue 4 arithmetic ops per cycle. So a cache miss could cost you 1,000 instruction issue slots. That means the performance model, the cost model, has shifted by a factor of 1,000 in the last 30 years. Now, what are the chances that the memory layout we had that was optimal 30 years ago is still optimal now? Pretty unlikely, right? And so if you look at the way Java lays things out in memory, there are these tiny little islands of data that are connected by pointers, right? Objects generally tend to be small. They have a small number of fields. They have an object header, which is often as big as the data they hold. And then they are connected by pointers. And that means you traverse that pointer and you're potentially paying for a cache miss. The reason this is the case is that all objects have identity. And this is the natural way to lay out objects with identity. But not all objects need identity. And they don't necessarily all want to pay for it. So, again, our trusty point class. If you think about how an array of points is laid out in memory, an array is an object, so it has a header, and then it has a bunch of pointers, and each pointer points to an object, which is a header, has a header, and then has some data. So as a data layout, this sucks on memory density, right? Because you're using 5 words of memory for each 2 words of actual data. So that's big overhead. It sucks on indirection, on locality, because every time you want to actually operate on data, you have to traverse a pointer, which may mean a cache miss. And as a special bonus, it makes a lot of work for the garbage collector and the allocator. So yay. Now, if I care, if the data I was working with was polymorphic, if it was mutable, then this layout is the cost I'm willing to pay for those benefits. But if these are simple, value-based classes, I shouldn't have to pay this. Now, some developers end up doing this. How many people here have done this? Yeah, it's kind of embarrassing, isn't it? Because they muck up their code so that they can get better locality. But the cost of that is less readable, less maintainable, more error prone. And the root cause of that is we gave you a bad choice. We said, here, you can have performance or you can have abstraction. Pick one. And whenever you get a choice like that, you have the chance to pick wrong. And whenever one of the choices is performance, you get twice the chance to pick wrong. And the problem is we can't automatically look at your code and say, oh, you never used the identity, so we'll give you a different layout. We can make some guesses sometimes, but that's kind of the history of that is kind of a sad story. So we need some help from the programmer to say, look, I promise, I'm just a dumb class, no polymorphism, no mutability, just my data, and then the runtime can give you a layout like this, which is most of the time the layout you want, gets you better density, better locality, and less allocation churn. So, what code do we have to write to get this? Well, not a big change. The current word for this is inline classes. These were called value classes. The name may change again. But you're basically saying, here's a class that is just its data. Feel free to inline it into other objects. Feel free to inline it into arrays. Don't try to reason about its identity because it has none. Compare them by their data, not by their pointer identity. And this is useful for a lot of things. It's not useful for everything, but it's again one of these trade-offs of by giving up identity, which means we're giving up mutability and layout polymorphism, we get this big benefit of the value. These types can be routinely flattened into arrays, into other inline classes, into other ordinary classes. We don't need to carry around an object header. So it's you get all the coding benefits of classes with all of the all of the performance benefits of primitives. So you can think of them as faster classes. You could think of them as programmable primitives. They're sort of both the same thing. We call this codes like a class works like an int. So they can have most of the things classes can have. They can have methods. They can have fields. They can use encapsulation. They can have type variables. but there are certain things they can't do. They can't have super types, they can't have mutable fields, etc. So who cares? My claim is everybody cares. If you're working with large data sets, well, you'd like to be able to pack more data into the same size heap. You'd like to be able to get better flatness and locality out of your data. If you're a library writer, you like to write abstractions like optional without having to pay the penalty of, now I have to make a box object to wrap around my value, and people don't like that, right? So you can have all the abstractive benefit for wrapper classes like optional or numerics or similar things without paying the runtime cost. You can have more efficient collections because you can reduce the number of indirections inside your collection implementations. Let's say you're Charlie Nutter, writes the JRuby compiler. Well, one of the biggest pain points for languages on the JVM that aren't Java is maybe your numerics aren't exactly like Java's numerics. And that means you have to use objects to represent arbitrary precision fixed nums. And now you're paying this boxing penalty for every numeric, and you're doing this heroic work to try to eliminate the boxes where you can. Well, if you could write them as inline classes, you wouldn't have that problem. If you have a language with tuples, inline classes are an ideal compilation target for that. If you have a language with multiple return, inline classes are an ideal compilation target for that. So my claim is everybody wants these things. They just may not realize it. So we've been running for a while. We've gone through like 5 rounds of prototypes. The latest prototype is actually good enough that you can design data structures with it and see big performance improvements. It's pretty cool. And there's an early access binary you can go download if you're interested. Just to give a quick a performance example, imagine you're doing matrix multiplication with complex elements. So you write your complex class, you open your complex analysis textbook, and you transcribe the multiplication algorithm into your code. So this is how I add complex, this is how I multiply them, and this is how I multiply complex matrices using a slow algorithm. And it's straightforward and it works, but then look at all the allocations everywhere. And every one of those adds and multiplies is an allocation and an indirection. If we say, let's make complex an inline class, none of this code changes. And everything gets compressed down to much less memory, much better locality, and laptop quality benchmarks, but we saw 12x speed up in time, 1000x improvement in allocation rate. And where does that come from? Well, part of it is not making so many round trips through the allocator, but part of it was we instrumented the instructions per cycle in our benchmarking tools, where in the box version, we were barely issuing 1 instruction per cycle. And even though we had the opportunity to issue up to 4 arithmetic ops per cycle, because the CPU was spending all the time waiting for data. By eliminating the indirections, we were able to push up instructions per cycle up to like almost a factor of 3. The CPU is spending most of its time actually multiplying numbers rather than waiting for the cache subsystem to cough up data. So obviously not all workloads are going to see this kind of improvement, but it also wasn't a lot of work to get this improvement. Well, it was like the incremental work of saying inline class complex was not a lot of work. The previous 5 years of investment was a lot of work, but you don't have to repay that. So let me sum up, and then I think we've arranged it so that I can take questions during the lunch. So I'm going to hang out here, and you can ask me questions. But if you're hungry, I won't be insulted, and you can go get food. But just to sum up, Amber has been delivering for several years. We'll continue to deliver, over the next couple of years with some really cool features, record seal types, pattern matching. Valhalla is finally starting to bear some fruit, and it's awesome. We were stuck in the lab for a long time, and now it's starting to get real. And Panama and Loom are also have made impressive progress in the last year. So our pipeline is better than it's ever been. It's a really cool time to be working on Java, and I hope it's a really cool time to be working with Java. So with that, I thank you very much, and I will take questions. All right, who's got mics? All right, Eddie's got mics.
Yeah. So, question about records. So, can records be generic?
Yes. Can records be generic? Yes. Yes, they can. They can have type variables. So if you want to declare, in our min-max example, if you weren't returning a pair of ints, but you wanted to have, min-max of t, where the two fields were of type t, yes, no problem.
And another question, so in the examples you gave for pattern matching with switch expressions, so there was a default clause, but then should can we have it like it has the default can simply be object type, right? So is that supported or?
Yeah, you can say case object, and then the compiler will do an analysis to say, is this pattern total on the static type of the target? And if so, it will recognize that you don't need to do anything else.
Hi. I actually have two questions. The first is actually for the Java team about the adoption of the features we've seen today. So I know we have a big logistical hurdle at Google, which is we're on a certain cadence for adopting JDKs. So I think it hurts us in two ways. A, it's harder for us to participate in the preview features because we'll basically not be able to use them while they're in preview until we get to the next JDK. And the other aspect is there are some features here, even if controversial, would actually help certain teams at Google, but it could be years before we see them. Concrete example, value types would actually concretely help the promise graph internals because we did all those awkward things of enrolling classes to get rid of pointers for performance and memory reasons. So value types would be a net win for us, but we may not see it for years. So just curious, like logistically, how are we addressing the newer cadence of JDK releases and their adoption at Google?
My job is to make this difficult for you.
Yeah. So this is a very good question. This is one of the reasons why we're trying to change our deployment model internally so that we can adopt faster. Today, we build in a lot of Google-specific features into the JDK that we run. Things like management and monitoring and other features. We want to upstream all of that so in some form or another so that we can take stock JDKs and use them. It's going to take us a couple of years to do that. And it's going to take help from Brian and others to make that possible. But we feel it. We understand the issue. We want to move faster, and there's some barriers. It's not a simple thing to solve today, but over the next 2 years, I hope that we can be using stock JDKs about the same time some of these features are mainstream.
Thank you. My second question is for Brian. You said like one sentence about concurrency, which piqued my interest, and then didn't talk about it at all. But you said, "Oh, I'm glad we dodged the bullet." Well, in my paraphrase, glad we dodged the bullet of async await. But like in Brad's talk earlier, a lot of the Loom and coroutine examples are semi-async await in terms of blocking on futures, et cetera. So, in your view, what is the paradigm that should be used in Java if it's not async await style?
Yeah, okay, great question. I'm going to follow up on John's thing, and then I will answer your question. So one of the things that we discovered quite to our pleasant surprise was moving to the rapid cadence was a lot easier than we thought. We had, when this was being pushed by our management of we need to be shipping more rapidly every 6 months, we all thought, you're crazy. Maybe we could do a year. We could never do 6. It's been, not only has it been easy, but it has been so pleasant because all of this release management overhead just evaporated. And so it's easy to imagine all the ways in which moving faster is just really hard, and it may not be as hard as it looks. We've been very pleasantly surprised by that. I will get to your question.
So the JDK 8 to 11 migration is probably the biggest migration that we're going to do because 8 and 11 are very different. I think after that, releases should be much easier to adopt. Another concern is that the more recent upstream versions aren't as well tested, and we've seen some breakages even with like 11, and I think like 12 and 13 and 14 are even less well tested. So it might be harder to adopt that sort of stuff unless we are actively participating in the community and like fixing this sort of stuff.
I like that part.
So one of the reasons why we want to adopt stock OpenJDKs more quickly is so that we can start running them before they're released. We have a lot of testing that we do here all the time, but it's always retroactive. By the time we find an issue, it's too late. Brian can't fix it. So
Right, not in the version you tested it on. We can
Not
fix
in
it
the version,
future
right.
version, but now you're still in the same.
but sometimes you can't even fix it in the future version because people depend on it.
Yeah.
So anyway,
Yeah, absolutely. So your question about concurrency models, I haven't forgotten it. It's an important one. So the whole async await thing is what I call wrapping a pillow around the hammer, which is to say, when someone's hitting you over the head, you just want the pain to stop. And you will imagine all sorts of partial solutions that seem more pleasant than being hit by the hammer. Like maybe if you wrapped a pillow around that hammer, it wouldn't hurt quite so much. But it still hurts. With async await, you have the problem of there's certain kinds of code you can't call in certain contexts. So you have the red method, blue method problem. And the pain of that becomes more and more obvious as you start to build big code bases with it. It's offering you a way to get out of the pain or reduce the pain, and it's attractive, but it's taking over your programming model in ways that you don't realize until it's too late. So the approach we're taking in Loom is let me roll the clock back to the mid-'80s. So in the mid-'80s, the way we did concurrent programming was, well, it was called asynchronous programming at the time. And most operating systems had a way of saying, I want to do an I/O, I want to do it asynchronously, so return immediately and fire off a completion interrupt in some weird limited context when the I/O completes. And typically, your logic didn't just do one I/O. When that I/O completed, you would look inside the result and say, oh, now I have to get this block off the disk. So you'd fire off another one of these, and it'd be this ping pong thing. And the code was utterly unreadable and impossible to debug. It worked, it was really cool, but it was really, really painful because you would look at your code base and you'd say, where's my application? I can't find my application. The application logic was completely obfuscated by the mechanics of asynchronous I/O. But it worked, yay. And then Threads came along. So now we're talking like early 90s. Threads came along and everyone said, oh, thank God. Right now I can write dumb sequential code, which is code that humans can read. And if something blocks, well, it only blocks the thread. It doesn't block the processor. So you just write straightforward, straight line logic, and you can read that, and you can debug it. And you can, your monitoring tools, your performance tools, your profiling tools, all understand method boundaries. They can tell where am I spending my time, et cetera. I think async programming, either with async await in the language or a lot of the reactive libraries, are kind of like going back to that mid-'80s programming model with a much nicer notation. But it's still fundamentally the same model, and you're still letting your reactive library control your programming model. And it might be better than running out of threads, but the code is hard to write, it's hard to read, it's very hard to debug. So the Loom approach is, okay, the problem is I can't have a million threads. Let's make threads light enough so I can have a million threads so people can continue writing sequential code or continue to call the sequential code that worked last week. It will still work this week on fibers. And I don't have to cede control of my programming model over to this reactive library. So that's the bet we're making. I think there's valid arguments to be made on both sides. I see you're making a face, so but that's fine. I totally understand. But we think rather than shoehorning people into these questionable programming models, if we address the problem at its root, which is threads are too heavy. They're megabyte scale entities. You can only have a few thousand of them. You can't have a few million of them. You remove that limitation, people can program the way that they're comfortable with and use the libraries they have. So that's our approach. More questions? Or everyone's hungry?
Some questions from chat.
Okay, question from chat.
The first one was, you mentioned that the preview feature There was one where it prevented you from making a mistake. What was that preview feature and what was the mistake?
Yeah, so that's a good question. So it's the multi-line string feature. So we started out with what I think was the wrong design center. We started out with a design center of raw strings. And it seemed like a very sensible but actually incorrect abstraction to say, well, multi-line is just a special case of raw where the new line characters are just other raw characters. And the problem of multi-line strings and raw strings are actually very different problems. And so we kind of went down the raw strings route, and we got to something that was kind of okay for multi-line strings, but it was something that didn't integrate well into the rest of the language, and it still had a lot of rough edges that we didn't like. And so even though we had iterated to a stable point, at the last minute we said, oh, I just don't like it. And we pulled it back, and we went back to the drawing board with a new design center, which is, it's really about multi-line strings, in part influenced by the data that you guys provided us, which is, of all of the things that could have been raw or multi-line strings in your code base, how many of them actually used non-printing characters other than new line? Turned out it was a vanishingly small, percentage. So we started with the wrong design center. We ended up with the wrong feature. And it didn't help that so many languages conflated the two. And that kind of lulled us into a false sense of confidence that we could conflate the two also. And thankfully, we realized it before we made a mistake.
Another question from chat. There was some unhappiness with the instance of and the type pattern. Why did you decide to do that and not flow typing?
So flow typing it's another one of those wrap a pillow around the hammer solutions. It solves the immediate problem, but it has very little expressive power beyond, I just want to switch over something that might be an integer or a long. Whereas pattern matching has much more depth, and in particular, it is much more compositional. So you can compose patterns with each other. I didn't show examples of this, but you can compose patterns in a way that says, is this thing a circle whose center matches this pattern that matches points? And you can express much richer criteria in one go. And so flow typing would have been a Band-Aid on the problem. It would have addressed the particular case of the code example I showed, but it wouldn't have done any more. Whereas pattern matching is something that goes much deeper and offers much more real abstractive power in the programming model.
And then one last question. What is the difference between a record and an inline type?
Great question. Okay, so records and inline types, the immediate thing you'd observe is they're both about modeling data. They both require your fields to be immutable. Aren't they the same feature? And they're related, but they're different. They're both about giving something up. Records, you say, I'm giving up the ability to decouple my representation from my API. It's about data modeling. I'm willing to accept the representation as being my API. What inline types say is, I'm willing to give up my identity. I want to be just my data. And for each of those things you give up, you get something in return. If you're willing to give up both of those things, you can get the union of those benefits in return. So you can have inline records. Makes perfect sense. In fact, a lot of records will be candidates for being inline records when we have inline types. So they're related, but they're making different semantic statements, and you get a different set of benefits from each.
Hello.
Oh, yep.
Thank you for the great presentation. Actually, Project Loom was presented to us last year at this summit as one of potential features for JDK 12. So I'm curious, what were the technical challenges that delayed the release, and are they solved now? What are the current challenges? Thank you.
So I don't know who said that, but it's a good illustration of why you should never make timing projections. I can't imagine any world in which anybody thought it would be ready for Java 12 unless we were back in the 3-year-long release cycle. So a year ago, we were definitely not. I mean, a year ago, Java 12 was like 3 months away, and we were never 3 months away. So I think someone just misspoke. I actually think the project is making amazing progress. And so in the last year, So about a year ago, the problems that the Loom team were focusing on were: is this possible at all? Can we take the stack of a running thread, serialize the contents of these stack frames off into the heap, and then lazily put them back on the stack when I go to resume the continuation? And that was something we had to prove that it could be done at all. And in the last year, having proved that it can be done, what we've been working on is performance, debuggability, monitorability, all of those things that you would want to have if you actually wrote a program with it, as well as iterating on what is the API model that we're exposing. So Loom has two main abstractions, continuation and fiber, and they exist at different levels. Continuation is down in the VM, and it's about thread stacks and stack frames, and how do I unwind stack frames and put them in the heap where the garbage collector can still find the object references and things like that. Fibers is a higher level of abstraction. It's more like the Java Lang thread class being exposed into programs, and that's the programming model that people are going to program to. And so one of the things we've been working on in the last year is, what should the fiber class look like? Should it extend thread? Should thread extend it? Should it be independent from thread? What should be the interop between fibers and the thread API, like thread locals and such, where the trade-off is, if fibers can emulate thread local, then more existing code just works. On the other hand, that becomes a design constraint for fibers that we might not want to carry around for the next 25 years. That's, I would say, in the last year, we've been focusing on performance, debuggability, monitorability, stability, and the fiber API. So big progress, but not done yet. I'm hoping another year, you'll see stable early access builds that you could actually run real applications on.
So in the Java 5 days, I heard all these war stories about how introducing a new keyword, the enum keyword, into Java was a disaster, and there would never be a new keyword in Java ever again. Was this fake news at the time, or did you somehow, how did you avoid this problem?
Yeah, so we've learned more about the problem since then. So the real disaster was making assert a keyword in 1.4. because that broke basically every testing framework in the world. By the time we got to 5, we realized the mistakes of what we had done in 1.4 and started to experiment with the concept of contextual keyword, where in certain contexts, the compiler sees, oh, here, this is just an identifier, but if it's in this position in the grammar, then it's then we're going to treat it as a keyword. We've learned a lot about how to apply these tricks effectively since then. So there are certain grammar positions where it's easier to put new identifiers, like sealed, right? Things that are already in the modifiers production where they're preceding a class declaration or a method declaration are much easier. The other end of the spectrum is sometimes people complain about, why did you reuse instance of for pattern matching? Why didn't you make a new matches keyword? And personally, I think instance of was the right choice from a semantic perspective, but even ignoring that, trying to make a new infix keyword that can appear in the middle of an expression is orders of magnitude harder than doing so with, say, a method modifier. So we've learned about what are the trade-offs of where can we cheat and where can we not cheat. We've also fleshed out the taxonomy of what's the difference between a contextual keyword and a reserved identifier. And they have, I mean, the only people that care are people who write the language spec and the compiler, but they have different trade-offs for what kind of compatibility consequences does stealing this word, have, on existing programs. So, for example, one of the things that we did in switch expressions, most of the time with the switch expression, you just say case this, arrow, and an expression. But sometimes you might need to do some statements where you call a constructor and then you call some setters and then you return the result. And there was a big debate over what should be the way to yield up a value from a composite block. And we went around and around, and we ended up picking yield as a contextual keyword there, which, like, some people really like, some people really hate, but it does have a compatibility consequence of if there is a method in scope called yield, we have a harder time disambiguating it. You have to disambiguate with this.yield or foo.yield or something like that. But we've gotten much better at understanding the trade-offs and putting them out up front. That's the basic answer. It's still hard. It's a lot of work. It's expensive. We try, so we try not to do it too much, but we at least understand how to do it now.
Hello, I'm curious. A lot of the features you mentioned are very similar to ones that are in Kotlin. I'm curious about what's your opinion of Kotlin, and how much do you guys collaborate with each other? Do you, is there a club you guys hang out in where you think up all these ideas? So.
Yeah. So thank you for asking that question in such a nice way. So yes. So the way I think about Kotlin is it's a nice retelling of the Java story. Just as C# was a nice retelling of the Java story 10 years earlier, right? Where a language that is fundamentally quite similar, a lot of the same values, a lot of the same principles, is able to look at what the sharp edges and pain points are, start over with clean paper and say, well, we're going to leave those sharp edges behind. And I think it is a nice retelling of the story. I don't think it's all that different fundamentally as a language than Java is. I mean, comparing Java to Kotlin, the differences are more superficial than comparing, say, a Java to Clojure, which is another language on the JVM that it offers a very different programming model. As far as who is borrowing features from who, it's programming languages, they share influences. For the most part, it's not that C# stole X from Java. It's that both Java and C# got their inspiration from C or Pascal or Modula or one of the languages that preceded both of them. So we have a large base of shared inspirations, and nobody complains that somehow that C stole infix arithmetic from Fortran, right? No one expects, no one feels like Fortran has this like intellectual property right ownership claim over the notion of infix arithmetic. Because it's natural for the user base that a language like C is designed for to use idioms that made sense in Fortran. And similarly, Java and Kotlin and Scala, we're all playing in the same space. We're all reading the same papers. Yes, we talk to each other also, but there's a lot of vectors by which these ideas, propagate. And to some extent, we're willing to let others experiment and say what was successful, what was not successful. 10 years ago, if I were in this room and you were asking that question, you would have asked the same question, except you would have said Scala instead of Kotlin. And 10 years ago, everybody thought Scala was the end of Java. Well, it didn't work out that way, but Scala was a great laboratory. They did a million experiments, some of which were successful that we learned from, some of which were unsuccessful that we chose not to learn from. We call this the last mover advantage. We're able to see what experiments are going on in languages that care less about compatibility. Figure out what makes sense to be inspired by, emulate, integrate, but put our own spin on it, because every language feature exists in the context of the language it's in, so that even if you decided to copy a feature from another language, it wouldn't really be a copy. It would be more starting with the first principles and integrated into your language. We had the opportunity to do that for the things that worked and not do that for the things that didn't work. And similarly, if you look at a lot of the features in Kotlin that people really like, so many of them existed as RFEs in the Java bug database from 10 years before Kotlin was a thing, right? So we're all inspired by each other. That's, shoulders of giants and all that.
I have sort of a follow-up question about the if X instance of var Y syntax.
Mm-hmm.
When I first saw that on the slide, my reaction was that's super weird and unnatural, because you have a variable declaration inside of instance of, inside of a Boolean expression. Yep. So since you live in the future, is that something that's going to start seeming natural to me, or is it syntax that you were kind of boxed into?
So I think it is something that will seem natural to you. When you say if X instance of point var X var Y, that expression is in the if header. And so there's a sort of natural scope for those variables, which is one or the other of the arms of this if statement, or switch statement, or whatever. So I think it will feel natural. It will feel like smoother nesting of, there are some times when you'd like to, take local methods, right? C# has local methods, Java doesn't. But so in Java, you have to declare all your methods at the top level of your class. And if you intend a method to only be used by some other method, you just make it private and you just accept the namespace pollution that comes with. But if you could declare it inside the other method, you'd probably enjoy that. You'd probably feel like there's a right place for this method and I'm putting it in the right place. My hope and belief is that that's how you will come to feel about bindings that are declared inside an expression, that they are being declared in just the right place that defines a sort of subscope of that statement, and they're actually not even in scope where they wouldn't be definitely assigned. So I think it is something that's new and different, but I think it is something you'll come to appreciate once you rewire your brain a little bit. Thanks.
Going back to Kotlin and the last mover's advantage and Java's priority on compatibility, as someone who's been working on Java or with Java for like 20 years, I can appreciate that. But do you ever see a future where erasure doesn't exist?
Yes, but so everybody loves the idea of having reified generics, and you know in most conversations that start with why doesn't Java have X, the implicit thing that's going on in the questioner's head is there are so many advantages to X, and they see the benefits and they don't necessarily see the costs. So there's a lot of cost associated with reified generics, and there are obvious benefits associated with reified generics. So if you look at it as a trade-off, one of the trade-offs you make with erasure is footprint versus type specificity. You know, in C++, if you have templates, you have a simple class list of T, and it turns into 60 megabytes of object code on disk because it's gotten instantiated, you know, for all these different types. So that's one trade-off. Another trade-off there is by templating out all those instantiations, the JIT is not necessarily able to see the commonality between them and has to independently compile them. It has more type information when it does that, but it's a lot more code to compile. That's pressure on code cache, et cetera. Another cost of reification is there's code that we all write, or not all of us. This is code that a lot of essential code that we use every day that does various cheaty things that couldn't be done with reified generics, or that could not be done efficiently with reified generics. And so there's a real cost of certain code idioms. They're just not practical to express in a performant way. And so those are the costs that no one sees. Everybody sees the benefit of, like, you know, they sort of have a mental model where they say erasure is, you had this perfect good type information, you threw it in the garbage, you idiot. It's actually much more subtle than that. So I view erasure as a very pragmatic trade-off. That said, do we see specialized generics in Java? Quite possibly. So if you look at what's happening in Project Valhalla, you saw the example I projected on the board. I didn't write anything on the board. I projected of the flattened array of points. And that's great, but what happens when you want to have an array list of points? You don't want to fall back to the boxed representation because array list is erased. So being able to have specialized generics for array list and hash map makes a lot of sense, not because the type information at runtime is so valuable as to be willing to pay that cost, but the layout benefits, the density and flatness benefits are substantial. So yes, we are looking at how to do specialized generics, you know, over inline types, for example. Some of the people who want to get, you know, to a non-erased world will be made happy by that. Some of them will be infuriated by the solution that we end up with, because the goal is not necessarily about making the type information available everywhere, and certainly not about enforcing the type information everywhere, because the VM has a different type system than the language does. And certainly, some people, when you ask them why they want reified generics, they get on their high horse, they talk about security. Type safety is about security. And you pull on that string a little bit, and you realize that you have to push all of the language level type checks down into the VM. And first of all, like, how happy would the Scala folks be about having Java wildcards pushed into the JVM? Not very. right? But secondarily, there are well-known undecidabilities in a lot of polymorphic type systems. Would we like to push undecidable subtyping checks down into the VM so that so there's a whole new category of denial of service attacks possible? No, I don't want to do that. So, yes, but yes, we want to get there. No, erasure is not this simple. You had a perfectly good thing in your hand, you threw it away because you were an idiot. It's not. It's much more subtle than that. But yes, we would like to specialize so that we can get layout polymorphism.
Thanks.
Long answer to a short question.
When we're gonna take like one more question,
Perfect.
and then we'll let everyone grab lunch and get back in here in time for the lightning talks.
All right, who's the lucky person?
One more question on the type system.
Yeah.
You've talked a lot about the new keywords that you want to introduce, the record, the inline. We already have the interface and the class. Are you considering making this a more general system where you can possibly also define a type of class with the following properties, as in can be instantiated or cannot be instantiated, has this memory layout? So I think there's a similar proposal going on for C++. It's called meta classes.
Yeah.
Are you thinking in that direction?
So we're not thinking about that direction, but we're thinking about a different direction, which is if you've done any work in Haskell, you know about type classes. So when you say class C implements an interface, what you're saying is that the instances of C conform to some protocol. But it's also useful to be able to say that the class itself conforms to a certain protocol. That's where features like collection literals, operator overloading, et cetera, come from, because by being able to say, integer conforms to the type class of monoid or ring or whatever algebraic data structure you care about, that allows you to then generify over, I can add, hand me a monoid, hand the instance of a monoid, and I can add them up for you and things like that. So we are quite interested in how do you abstract over class behavior, and you mostly end up with something that looks a little like Haskell's type classes there. But we're more interested in abstracting in that direction than trying to unify class, enum, interface, etc.
All right. Thank you, Brian, for the great talk and for this very interesting Q&A.
Thank you.